Good afternoon, ladies and gentlemen. My name is Minh. I'm a PhD candidate in University of Information and Communication Technology, Thái Nguyên University, Thái Nguyên, Vietnam. It is my great honor to present my research on the topic of structure of six-dimensional fine non-commutative algebras with many single side units. These studies focus on exploring fine non-commutative algebras and their potential application in post-quantum cryptography, a highly relevant and critical field in the current cryptographic landscape. Last, let us begin by diving into the background and theoretical foundation of this research. Let me now walk you through the structure of this presentation as highlighted in the overview slide. The report is organized into the four main sections. The first is introduction, and next we define FNAAs, examine their theory properties, and highlights their relevance to post-cryptography. We present our proposed post-quantum digital signal algorithm, detailing its design, implementation, and verification process. Finally, we summarize our key findings and outline future research transition to future intent and the practical and security of FNAAs in cryptographic systems. The brain objects is to analyze the structure of six-dimensional fine non-commutative algebras and invest their application in public key cryptography, particularly in post-quantum digital signal schemas. However, this research also led to significant changes. The language publication in extinct multiple arrays cryptosystem, which limits their particular usability. Ensuring security in quantum computing environments with demand robust and effective solution. The objects and changes from the foundation for the methods and research that I will present in the subsequent slides. Now, let's delve into the format definition of finite associative non-commutative algebras, or FNAAs for short. FNAAs are m-dimensional vector space over the finite files GFP, where the multiplication organization is distributed but not commutative. Mathematical for two vectors A and B. A dot B is divided as a double submultiplication from E equals 0 to 5 and Z equals 0 to 5 of A sub I multiplied by B sub Z times the product of E sub B and E sub. Here how this works. The vector A and B are represented as A is a summation from E equals 0 to 5 of a sub I times E sub E, and B is summation from G equals 0 to 5 of B sub G times E E sub G. A, I, and B, Z's are the coordinates of A and B of the vector in GFP. the finite files. EI and EZ are the basic vectors. The term E sub E sub 0 refer to the product of two basic vectors, which can be simplified into single component vector using the table of basic vector multiplication or TMBV sort. The structure forms the mathematical foundation of FNAAs and the non-commutative property, which is critical for designing a secure post-quantum cryptographic algorithm. Now let's discuss the key concepts central to the first single-side units in FNAAs and the Hidden Discrete Logarithm Problem. A single-side units in FNAAs are separate elements in a non-commutative address that on side multi-cap property. Formally, they are defined as A psi x equal A or A psi A equal A, depending on the whether units operating on the left or the right side. The element are crucial for constructing secure cryptographic systems based on FNAAs. The hidden discrete logarithm problem is defined as the chance of solving the equation E equals A raised to the power of x. To find x where A belongs to a non-commutative address like FNAAs. This is computationally hard problem, meaning it is difficult to solve experimentally, even with the power of quantum computer. Because of this difficult, the HDLP provides strong security quantities against quantum attacks, making it excellent foundation for post-quantum cryptographic algorithm. In this slide, we look at the three types of FNAAs that we analyze in the research, each with varied number of single-side units. The first FNA with the P power 2 single-side units, the FNAs were found to be secure and stable, making them ideal candidates for cryptographic application. Their structure and solution to computation attacks, particularly in post-quantum settings. The second FNAs with P power 3 single-side units, the FNAs are insecure, primarily because they map to commutative subalgebras. Such mapping reduces their complexity and makes them vulnerable to attacks, rendering them unstable for cryptographic purposes. Finally, with the P power 4 single-side units, similar to P power 3, CANAs are also unstable for cryptographic use. Their structure does not provide the necessary security guarantees, which makes them insecure cryptographic implementation. From the finding, we conclude that FNAs with P power 2 single-side units are the most promising from secure cryptographic system. Next, I will show how we leverage this structure in our proposed digital signal algorithm. Let's now focus on the characteristic of FNA with P power 2 single-side units, the most secure and stable type we analyze. Characteristic of P power FNAs units are given as a formula error. This structure provides system and compact way to define the single-side unit with a culture for maintaining the identity of the average. A core property of P power 2 FNA is the non-commutative equivalence through basic vector multiplication. Mathematically, this is expressed as EI cycle EZ equal lambda EK, Here's a multiplication of basic factor bridge a scalar version of another basic factor. Maintaining the non-commutative supply essence for the cryptographic application. Now let's explore the characteristic of FNA with p-power 3 and p-power 4 single-sign units. The units in p-power 3 FNAs are represented as a formula R, with these FNAs maintain the algebra structure. The inherent mapping to commutative subalgebras weaken their cryptographic potential. With similar charge, the unit in P4, P-power 4 FNAs are defined as a formula R. Unlike P-power 3, this type will also map to commutative subaddress with limits in the definition for secure cryptographic system. Both P-power 3 and P-power 4 FAM map into the commutative subaddress, making them unsuitable for cryptographic application. This mapping reduces their complexity and makes them vulnerable to attacks. Due to the limited P-power 3 and P-power 4 FANs cannot be efficiently utilized for cryptographic purposes. Instead, we focus on P-power 2 FANs which provides the repeated security property. Next, we see how P-power 2 FANs are applied in the design of our designing secure algorithm. Let's now summarize the key finding our analysis highlights the channel in elimination of defined type of FANs. For FANA with p-power 2, suitable for secure postquantum single schema, the structure and property makes them excellent choice for cryptographic application. Maintain non-commutative property. This is a critical feature that ensures security and effectiveness in quantum environments. With a finding for FANA with p-power 4 and p-power 3 is not suitable for cryptographic use. Post p-power 2 and p-power 4 FANAs map into the common suitable. This mapping composes their secure and makes them infected for cryptographic system. In conclusion, P-power 2 FANA are the most mean option for design secure post-quantum cryptographic algorithm. This sets a following for design digital switcher algorithm with the Teknik. This is a purple digital signal algorithm. The first step in our purple algorithm is key generation. We begin by randomly selecting some pattern parameters and define private key components. From this, we compute a set of public key vectors that incorporates the non-commutative structure of FANs. The public keys form the foundation of the cryptographic system, ensuring security and unequivocity. In the second step, single generation, we create a single sign vector tied to the message being signed. Using this vector, we calculate a hash values. It has values and addition parameters that link the messenger private key and single process. The result is a signal that undergoes represents the messenger with while maintaining cryptographic integrity. In the final step, we output the signal we consider a multi-compass components that ensure both security and efficiency. Our algorithm levels the prototype of FNAA to optimize performance, requiring only a major number of computation. This balance between computation efficiency and security makes it suitable for real-world post-quantum application. The final part of the algorithm is the verification process, which ensures the validity of the digital signal. The hash calculation first we calculate a hash value from the signal to verify its authenticity. And next, we use the signal component to contrast a verification vector. This vector is used for cross-checking the signature validities. We then compute a new hash from the document and the verification vector. If this hash match the one derived early, the signal is considered valid. The system checks whether the two hash values are equal as match confirms the signal's authenticity, otherwise it rejects. With computation complexity, we require 7 exponential to 1 to 8 bits easy in the 6-dimensional FNAAs. Now let's look at the key advantage of the purple digital signal algorithm, which make it highly suitable for post-quantum cryptographic application. By utilizing FNAA with p-power 2 single-sign units, we achieve even case sign optimization. This makes the algorithm particular for real-world users without securing security. The algorithm leads the indirect non-commutative property of FNAs and the computation hardened of the Hidden Discrete Logarithm Problem. The future answer robust protection and against both classical and quantum attacks. By emulating Algebras multi-property cryptographic MPKC principle, the algorithm is designed to resist attacks from quantum computers, making it a future-proof solution. The combination of efficient security and quantum reason posted our algorithm a strong candidate for next generation cryptographic system. While our purple algorithm demonstrates significant advance, it also comes with some limits that are important to address. FNAs with p-power 3 and p-power 4 single-sign units are not suitable for cryptographic use because they map into commutative subalgebras. It reduces their security and limits their applicability in the secure system. The higher dimension in FNAs, while enhancing security, also lead to increased computational costs. This can pose chances for implementation in resource-constrained environments. To address that issue, future research could focus on optimizing parameters to minimize computation complexity while maintaining security. Understanding these limits helps us identify for future improvements, ensuring the particular and robustness of FNAs-based cryptographic system. Let's now explore the application of our purple algorithm, which span multi areas in cryptographic and real-world systems. The algorithm they design a secure digital signal schema, ensuring authentic and integrity in communication. It also enables secure key exchange protocol in quantum environments, address the chances proposed by quantum computing. Our works contributed to the development of a cryptographic algorithm based on edu.vn. Thank you.